Have you ever wondered how unlike charges attract each other? What goes on in the space between them that allows them to have this effect on each other? In this presentation, we propose a mechanism that explains how attractive and repulsive electrostatic interactions occur. In quantum electrodynamics, attraction and repulsion are caused by the exchange of virtual photons between charged particles. This makes sense since such exchanges would change the momentum of the two charged particles involved in the interaction. Since force is directly related to change in momentum, these changes could give rise to the forces associated with attraction and repulsion. Conceptually, it is easy enough to imagine repulsion resulting from the recoils as similarly charged particles throw virtual photons at each other, just as two spacemen approaching each other in space can slow their approach and even turn it into a retreat by throwing a ball back and forth. But try to imagine a particle exchange mechanism that could result in an attractive interaction. To my knowledge, it has never been done. We suggest a model that provides an easily understandable mechanism for attractive and repulsive electrostatic interactions. Fundamental to this model is the notion of a vacuum virtual pair. In quantum electrodynamics, particle-antiparticle pairs randomly pop into existence in the vacuum in violation of the principle of conservation of energy. This is allowed as long as they don't last long enough to be observed. To be observed, they would have to last longer than the uncertainty principle limit, h/2mc², where m is the mass of the species involved, h is Planck's constant, and c is the speed of light. Such pairs are called virtual pairs. We say that the vacuum is seething with virtual activity. The mechanism that we will propose in this talk involves a new and fundamental assumption about the order in which virtual pairs are produced in the vacuum. The particle, say an electron, it's indicated by red at the center of this diagram, is surrounded by virtual particle-antiparticle pairs. Each virtual pair is polarized so that the virtual antiparticle, the green one, is closer to the polarizing particle than the virtual particle, the red one. Much the same way that a polarizable medium is polarized by the presence of an electric charge embedded in it. The component particles of any given virtual pair can be thought of as being static for their brief moment of existence, or moving apart until they fade from existence, or moving apart and then coming back together to annihilate each other. Any of these mental pictures is acceptable as long as the spatial extent of the virtual pair does not exceed h/2mc and it exists for no longer than h/2mc². Three concentric circles of virtual pairs are shown here as though they exist simultaneously, but they don't. The inner circle exists first, then the next circle, etc. As one circle fades from existence, the next circle is created. The analysis begins by considering what interaction-specific information the virtual photon must carry as it transits. The analysis then centers on the vacuum polarization loop diagram. So let us proceed. What interaction information must the virtual photon carry? This slide shows the virtual photon gamma located between a negative emitting particle and a positive absorbing particle, and it asks the question, in this part of its existence, what information could the virtual photon logically be carrying? It makes sense that it could be carrying the charge information for the emitting particle. After all, it was just created by that particle and was just in its presence, so it could certainly know its charge. Logically, it could not carry the charge information for the absorbing particle since it has not yet approached that particle. At this point in its existence, it doesn't even know if there will be an absorbing particle. All it knows at this point is the charge of the emitting particle, and it will need to carry that information to the absorbing particle so it will know what kind of interaction to mediate when it gets there. If the charges are alike, it will need to mediate a repulsive interaction. If the charges are opposite, it will need to mediate an attractive interaction. And we must explain how it mediates these interactions. In this presentation, we are considering only elementary interactions. These consist of one particle on either side of the interaction. An example of a more complex interaction would be the attraction of an electron of charge -e to a nucleus of charge +Ne, where N is the number of protons in the nucleus and E is the magnitude of the charge on an electron or a proton. Such a complex interaction is easily analyzed as the sum of n elementary interactions, so we need only consider elementary interactions here. In an elementary interaction, the magnitude of the charge is always E for both charges, so the virtual photon doesn't have to carry that information. It need only carry the polarity of the charge of the emitting particle with it as it travels. The equations of quantum electrodynamics are complicated and can only be solved by approximate methods such as perturbation theory. In the version of perturbation theory used in quantum electrodynamics, Feynman diagrams are used as an aid in writing the terms of a power series solution to the equations. Two classes of diagrams exist: tree diagrams, which have no loops, and loop diagrams, examples of which are shown. Both types must be included in any calculation in order to get results that are correct. The loop diagram shown in this slide has the virtual photon leaving its emitting particle on the left and spawning virtual particle-antiparticle pairs, the loops, before arriving at its absorbing particle on the right. These pairs represent the polarization of the vacuum by the charged particle that emitted the virtual photon. As such, their polarization is longitudinal. The fact that we have to include loop diagrams of this type in order to get the correct results for our calculations means that polarized virtual pairs in the vacuum are part of what we call virtual photons. This brings up a question. What part of what we call virtual photons are virtual pairs? Are polarized virtual pairs a small part of what we call virtual photons? A large part? Perhaps virtual photons are composed entirely of polarized virtual pairs. Since the polarization direction of the virtual pairs corresponds to the polarity of the charge of the particle that emitted the virtual photon, the vacuum virtual pairs are capable of transmitting the information needed to mediate the electrostatic interaction, namely the polarity of the charge of the emitting particle. The virtual photons are also capable of transmitting this information via their longitudinal polarization state. Let me point out that while real photons are limited to transverse polarization, virtual photons are not. There exist virtual photon states that possess only longitudinal and scalar polarization. While these states contribute to neither the fields nor the amplitudes, they do contribute to the term in the photon propagator responsible for the Coulomb interaction. There are two problems. The information needed to mediate an electrostatic interaction, namely the polarity of the charge of the particle that emitted the virtual photon, is carried by both the longitudinal polarization state of the virtual photon and the polarization of the vacuum virtual pairs that accompany the virtual photon. Nature usually avoids this type of redundancy. While this first problem may be no more serious than offending some people's sensibilities, this next problem does more than offend sensibilities. For an attractive interaction, the momentum imparted to the charged particle that absorbs the virtual photon is necessarily in the direction opposite the direction of the photon's motion. We are asked to believe that a simple particle, a photon, can impart momentum in a direction opposite its direction of travel, when clearly a more complex system would be required to achieve such a transfer. Whatever rationale is offered to explain how the mathematics allows the virtual photon to transfer momentum in a direction opposite its direction of motion, that rationale is only telling us how the mathematics is being used to give the correct result, even though the physical picture clearly does not work. Our simple conception of a virtual photon as a photon that is not on the mass shell may be mathematically adequate, but it is not physically adequate. A virtual photon is not simply a particle moving in a given direction, but is more like a system or structure that carries information along a certain track and imparts momentum in either direction along that track when it arrives at the absorbing particle. We need a better picture. As witnessed by the vacuum polarization loop diagrams, virtual photons are always accompanied by polarized vacuum virtual pairs. Otherwise, calculations would not give the correct results. Also, the vacuum virtual pairs that accompany virtual photons need virtual photons at their locations to know what polarization direction to assume as they come into existence. They cannot get that information from the real photons because they are transverse and do not carry longitudinal polarization information. Thus, virtual photons and polarized vacuum virtual pairs always exist together along common space-time tracks. You will not find these polarized vacuum virtual pairs away from virtual photon tracks, nor will you find virtual photon tracks devoid of polarized vacuum virtual pairs. That's the where of it. Now let's consider the when of it. Each virtual pair comes into existence when and only when the virtual photon is at its location. Hence, as the virtual photon propagates along its track, so does virtual pair production. Thus, virtual pair production in the vacuum is ordered, not random. There can still be randomly oriented virtual pairs not associated with virtual photons, but they are not part of this mechanism or this discussion. It is possible that the virtual pairs transmit the polarization information directly to each other, since they always come into existence next to an already existing pair. If this is so, then the logical need for a separate entity called a virtual photon is eliminated. So the two, virtual photons and virtual pairs, can be considered to be equivalent. Polarized virtual pairs are the physical manifestation of the virtual photon. These arguments point uniquely to a model which the following slides will elucidate. A better picture. The vacuum polarization loop diagrams modify the photon propagator. That is a fact, but how do we interpret this fact? In light of the previous discussion, we propose that this modification be interpreted physically as meaning that virtual pair production is occurring contiguously along the virtual photon's track, propagating through space along the virtual photon track as a virtual photon, transmitting the charge polarity information needed to mediate the interaction, and mediating the interaction at the site of the charged particle that absorbs the virtual photon by bracketing it between virtual pairs that it interacts with via vacuum exchange scattering, a process described on the next slide. This exact mechanism will be made clear throughout the rest of this talk. This proposal can be implemented by making the following minimal assumption. If the production of virtual pairs is ordered so that each pair triggers the production of the next pair adjacent to it along the line of polarization as it ceases to exist, then the polarization information would propagate outward in a line from the emitting particle at the speed of light. The virtual pairs transmit the polarization information directly to each other by always coming into existence next to an already existing pair. Every virtual pair would know the direction it is supposed to be polarized in, because every virtual pair would be a link in a causal chain of virtual pair production. I call this a minimal assumption because it's all we need to understand electrostatic interactions. It is also all we need to derive the Lorentz transformation, derive an energy-time uncertainty relation, obtain Newton's laws, and possibly derive Maxwell's equations. See the website orderedvacuum.com. But it is not enough to explain wave-particle duality or to have the virtual pairs serve as a medium for a de Broglie pilot wave, because it doesn't diffract. A more elaborate assumption regarding vacuum order would be needed to accomplish that goal. Since the standard interpretation of quantum electrodynamics has virtual photons being emitted in all directions from a charged particle, these causal chains must propagate in all directions from the particle. A particle immersed in such a vacuum would find itself surrounded by virtual antiparticles, so it would undoubtedly interact with the vacuum through vacuum exchange scattering, a process wherein the particle annihilates the virtual antiparticle of a vacuum virtual pair, leaving the virtual partner of that pair to carry on as the original particle. The new, previously virtual, particle is immediately surrounded by virtual pairs and undergoes another such exchange. Since each step requires time, h over 2mc squared, from the uncertainty principle, this occurs repeatedly with frequency 2mc squared over h. Result? A random walk with step size h over 2mc, random step direction, and frequency 2mc squared over h, which Schrödinger called Zitterbewegung. It is important to note that Zitterbewegung in an isotropic vacuum causes no overall motion. The particle is just as likely to go in one direction as the opposite direction. Not so for an anisotropic vacuum. Vacuum anisotropy is caused by the presence of other particles, and it causes motion by biasing the random walk. Each particle's random walk becomes biased by the anisotropy introduced into the vacuum polarization field because of the presence of the other particle, by way of the virtual pairs that the other particle adds to the vacuum. The virtual pairs from one particle bracket the other particle, biasing its random walk. This is how interactions occur in this model. Are the random walks biased toward each other or away from each other? To see how this works, an electron and a positron are shown along with their contributions to the vacuum polarization field immediately surrounding them along the line joining them. The other virtual pairs are not shown since they are not relevant to this step of this interaction. The electron's contribution is shown in green and the positron's contribution is shown in red. This is a schematic diagram, so don't attribute any significance to the distances and scales. Consider the electron. When it looks to the right, it only sees one virtual positron that it can annihilate, and that's from its own contribution to the vacuum. But when it looks to the left toward the positron, it sees two possibilities. Two virtual positrons that it can annihilate, one from its own contribution to the vacuum and one from the positron's contribution. Which one it annihilates depends on many factors, but statistically the next step of its random walk is more likely to be toward the positron than away from it. When the positron is considered, it has more possibilities to annihilate on the right than on the left, so its random walk is going to be biased to the right toward the electron. Thus both particles bias each other's random walks in a symmetric way toward each other. Note the implication of Newton's third law in this symmetry. It is not difficult to show that the resulting motion is accelerated. This is demonstrated in the PDF concerning inertia and Newton's laws on the website orderedvacuum.com. Thus, they attract each other. Repulsion is analyzed in a similar way. Two electrons are used for this demonstration. It is clear that there are more possibilities for annihilation on the outside than on the inside. Thus, both particles have their random walks biased away from each other. Thus, they repel each other. Well, that's it. That's how electrostatic interactions work in this model. Now that we have demonstrated the usefulness of the concept of causal chains of virtual pair production as a physical interpretation of virtual photons, and demonstrated the mechanism for electrostatic attraction and repulsion using these causal chains, we are done, and this talk is concluded. Thank you for listening.